So dear students, in this video, I'll be talking about the normalized and orthonormal wave function. And, and to start with, if we go back to any physical problem we come across, where the particle is bound by forces. You have a particle, it's bound by forces to a limited region. And the examples of this kind is the electron in an atom, right? And the particle in a box. We have a box. We have a particle in a box with impenetrable walls. This particle cannot leave the walls of this box. Now, in such cases, the probability of finding the particle in the entire space that we have, this probability of finding the particle in the entire space we have, can be written down as, can write down that as the integral of psi r and t square d tau equal to 1. Where this integration, that's over here, this integration is extended to all space. It's extended to all space. All space. And this equation can also be written in terms of psi r of t, psi star of r and t, d tau equals 1. Now, since the particle is somewhere within this box, that's why the integration the integration over this probability density should give us 1. And getting this 1 by integrating this integral over the whole space, we call this as normalization. Now, a wave function, if I have a wave function that I have written down here, if this wave function satisfies this condition that we have, that the integration over this whole space is equal to 1, we call this as normalization to unity. We call this as normalized wave function. Now, suppose the particle is bound to the limited region, as in case of the particle in a one-dimensional box. Say, for example, the probability of finding this particle at infinity is 0. So this psi star that we call as probability density, it is at x plus minus 1, at plus minus infinity, its value is 0. So this psi star is immediately equal to 0 at infinity. Now, any solution of the wave equation may be normalized. We have a solution of a wave equation, and we can normalize that solution by multiplying or dividing a constant. And it can be easily seen that the result that we obtain is also the solution of the wave function. Now, for example, if I take an example, say for example, if the function psi I have the wave function psi, and it has the coordinates x, y, z, and it satisfies the Schrodinger's equation. And the integral of the probability distribution over the entire space for this wave function comes out to be, say, n. It comes out to be n. So what should I write? Say integral psi star d tau comes out to be n. Now all I can do is I can bring that n here. Okay, so this is psi star d tau equals 1. And I can think of writing it 1 by root n psi 1 by root n psi star d tau is equal to 1. So then what should I say here is that I have got the normalizing factor. So what is normalizing factor in my case is 1 by under root of n. And I have the normalized wave function. I have the normalized wave function. And what's that? And that wave function is psi by under root of n. And as we understand that this 1 by under root of n, it's a constant. It's a constant. And is independent of the coordinates of x, y, and z as we proposed, as we started from here. And psi that we have, it satisfies the Schrodinger's wave equation. Then it's evident that this psi by under root of n that we have will also satisfy the Schrodinger's equation. Now, if we move on from here, and if I have, say for example, I have psi I and psi j. Now these are the wave functions. These are two different wave functions, and both being satisfactory solution of wave equation for the given system. Then these functions will be normalized. I mean, this is the solution to the wave function, to the wave equation. This is also the solution to the wave equation, right? Then these functions that we have, these functions can be normalized. I mean, integral psi I star psi j d tau is equal to 1. And integral psi j star psi I d tau is equal to 1. So they can be normalized because both of these wave functions are the solution. They satisfy the wave equation. They satisfy the Schrodinger's wave equation. Now, if the two wave functions that we have here, psi I and psi j, are such that the integral over this or the integral over this over the entire space, if it vanishes, if we integrate this thing or we integrate this thing, and the end of the both situations vanishes, they vanish. So if they vanish, then what I say is that, so that means if I have integral psi I star psi j d tau equal to 0, and I have psi j star psi I d tau equal to 0, then what I say then this psi I and this psi j, these two wave functions are called as mutually orthogonal wave functions. So these are mutually orthogonal wave functions. Now, in the next video, we would like to see, we would like to have the proof of this orthogonality condition of the wave function.